Hey everybody, sorry I'm a little late. I got caught up doing something else. It's good to see you all. Okay, I'm gonna go ahead and share my screen and jump into it. Can everybody hear me okay? I'm assuming I'm in my office, so a little bit of a different setup today. All right, awesome. Okay, so today I'm going to give a lecture on the materials of the seafloor. So if you look on the website, the Google site, this is the one I suggest that you do next. So I'm going to go over sort of what to expect in this lab. And if you see me looking off this way, it's only because I've got my laptop and then I've got like 2 other screens. So I'm trying to organize myself. So, all right, let me start this up. Okay, so let me also get this meeting controls out of the way. So there are 3 main types of ocean deposits, and these vary depending on where you find them in the ocean. So the 3 main types are lithogenous, biogenous, and hydrogenous. So we're first going to talk about lithogenous deposits. So the types of lithogenous deposits are terrigenous, volcanogenic, and cosmogenic. And so lithogenous stems from litho, which means like rock or pieces of rock. And so all lithogenous deposits are an organic material. They're made up of clasts that come either from the land or come from sea volcanoes or come from like meteorites or meteor deposits. So terrigenous specifically derives from land, right? Terra, land, terrigenous. Volcanogenic is derived from volcanic islands or underwater seamounts that are active, right? So volcanic. And then same with cosmogenic, right? Cosmo means space. It's derived from meteorite fragments. So if you're ever confused about, I totally forgot what these things mean, just look at the root word, right? Terra is land, volcano is volcanic, and cosmo is space, so meteorite fragments. So a lot of terrigenous material, actually almost all of terrigenous material, is transported and deposited by turbidity currents. Turbidity currents are gravity flows. So unlike when you think about landslides or alluvial fan deposits, turbidity currents work almost in the same way, but they're triggered by gravity. So what happens is you have a river flowing from the mountains all the way to the sea, and it gets deposited off the shelf. And it sort of sits on the slopes. You guys should be semi-familiar with those words from last week's lab. So it sits on the slope, and it sort of keeps building and building and building and building up. So if you guys ever built sand castles at the beach or sand castles anywhere else, or like mud pies, you'll know that you can only get them a certain height before they fall over, right? So the same sort of thing is happening with turbidity currents. This river, can you guys see my mouse? Maybe not. Okay, yeah. So this river is bringing down sediment, and it's depositing it right at the slope. So as it's depositing it, it's packing all of this material onto each other, and eventually it gives way due to gravity because it can only hold up for so long, and it flows down the slope and it deposits onto the basin floor. So you've probably seen this shape, this fan shape in other places, right? It happens in deltas, so the Nile Delta, the Mississippi Delta. It happens with alluvial fan deposits. It happens basically with any sort of sediment transport. It flows in a pretty straight line, and then once it reaches the basin, it fans out and creates this sort of shape. So the reason why it creates this shape is because as it's flowing down the slope, it's got a lot of gravity, right? Gravity is working in its favor. It's bringing it down this relatively steep slope. And then once it hits the basin floor, gravity sort of stops working, right? I mean, gravity is still working, but because it's on a basin floor, there's no longer anywhere for it to go down. So instead, it fans out. So biogenous ooze, which bio means life, right? So it forms from life-like materials or life, what do I want to say? Sorry. It forms from organic material, not life material. Sorry, it's Monday. And it's composed of more than 30% of skeletal debris. So this is sort of blowing up for you guys what this stuff looks like that creates this biogenous ooze. So this is like several microns blown up. In real life, you'd have to use a telescope to see this stuff, and a high-powered telescope. So there's two types of biogenous ooze. There's siliceous and there's calcareous. So siliceous is from silica, right? So it's made of diatoms and radiolarians, which are just small microfossils, and calcareous ooze, which is made from foraminifera and coccoliths. So this is all going to be like, how am I ever going to remember this stuff? And it just takes practice. So diatoms and radiolarians, the reason why they make siliceous ooze is because their skeleton is made of silica. So unlike us, right, our skeleton's made of calcium, a lot of calcium. Their skeleton, our skeletal material is made of silica. However, foraminifera and coccoliths, their skeleton is made of calcium, so they make calcareous ooze. Does that make sense? The reason why they make different oozes is just because of what their skeletons are made up of. And since the biogenous oozes are composed of more than 30% skeletal debris, that's why it relies so heavily on what their skeletal makeup is. Okay. So because their skeletal makeup is different, and those different organisms are found at different places in the ocean, we can use where they're found to determine what the seafloor used to look like. So calcareous oozes are not found any lower than 4,500 meters. So right here, there's the CCD line. And what that is the calcium compensation depth. And so because of cold temperatures and a higher salinity sinks, pressure increases, and then therefore so does the solubility. So what that means is when pressure increases, all that's left below this line is siliceous ooze. Okay, because all of the calcium has been absorbed in the water. Okay, so here's sort of a really good example of what you'd see. So here we've got our mid-ocean ridge, and all of these calcite secreting warm water organisms are up at the surface, and when they die, they settle down towards the ocean floor. Okay, as you all, my mom's calling me right now. Not a good time, Mom. So as you all know from last week's lab, the mid-ocean ridge is a spreading center, right? It's diverging apart. So these two arrows, so new crust is being made, and this portion of the ridge is diverging apart. It's moving apart from each other. So all of this calcite secreting material that was laid down here is moving this way. It's moving off the ridge, okay? And so as it's moving off the ridge, it's getting closer and closer to the CCD, okay? Closer to that 4,500 mark. And remember, below 4,500 or below the calcite compensation depth, all of the calcite material gets absorbed into the water. And so all that's left is the siliceous material, which can't be absorbed. Okay, so everything below the CCD has to be a siliceous ooze. So if you find that calcareous ooze below 4,500 meters, that just means that it's been moved from a higher depth, or sorry, from a lower depth or a higher elevation to this lower elevation. Does that make sense? I can go over it again, just let me know. But I'm going to take silence as understanding. Okay, cool. So just once more, if you find calcareous ooze, like right here, below 4,500, it just means it must have moved from a higher place. Okay, so this ooze was once up here, right? But because it's been diverging, it has now moved to a lower place. And that's why the siliceous ooze is on top of it now, right? We don't see any siliceous ooze up here, but we do see it here. Okay? Okay. Above 4,500, you have calcareous ooze. Below, you have siliceous ooze, unless it's been moved from a higher place. Okay? Alrighty. So the third type, I spelled this wrong, is hydrogenous deposits. So these form from chemical precipitations from seawater, right? Hydro, water. This is chemical precipitations from the seawater. So a really popular one is manganese oxide precipitates. And they're mostly what you're going to find in seawater. You'll find other precipitates in springs or river water or basically anything that's not salty, but in salt water and seawater especially, you find manganese oxides. Have you guys ever seen those photos of Yellowstone where the springs have these crazy beautiful colors? All of those colors are from precipitates. All of those colors are hydrogenous deposits. Okay. So manganese oxide precipitates, or these hydrogenous deposits in seawater, start at a nucleus of some skeletal or mineral matter, and then they grow around it, right? So these little dots here are all some sort of little mineral deposit, or little mineral material or skeletal material, and then it grows around it. It's sort of like a pearl, right? Do you guys know how pearls are formed? Basically, sand gets into an oyster and it irritates it. And so in order to protect itself, the oyster secretes this deposit and it grows around the thing that's bothering it, that little sand material. And then we get this beautiful pearl, right? This is the same sort of idea, except instead of a oyster secreting it, it's the seawater depositing this manganese oxide. Okay, but it just doesn't deposit it out of nowhere. It needs some sort of skeletal material, some sand matter to grow around. But that's why it grows in this really cool circular or ellipsoid pattern. Okay, so that's the end of the slideshow, but I want to take you guys to the lab so that we can talk about not that. I don't even know what that is. This. All right, so materials of the seafloor is what I suggest you guys do this week. And remember, use this answer sheet to complete the lab. And so this is where it talks more in detail about lithogenous deposits. And I want you guys to pay some attention to, hold on, let me hide these meeting controls again, about where it's talking about these deposits. So remember we talked a little bit about those turbidity currents, but they have to get to the sea, just the seashore in some way, right? And usually that way is from rivers. And so as geologists, you can tell how long or about how long a clast has traveled depending on the roundness. So if it's really angular, it probably hasn't traveled very far, right? Because it's not very broken down. If it's really rounded, it usually has traveled very far, right? All of the rough edges have been grinded off of it, and now it's relatively round and well, you could say it's well traveled, but it's traveled from a far place. Does that make sense? Why very angular would be from a shorter distance and rounded would be from a farther distance? Does that make sense? Okay, cool. You can also tell from how well or poorly sorted it is. So if I have, so imagine I put water, mud, and sand in a bucket, and I leave it there for a couple days. What's going to happen to the sand and the mud? Is it going to remain super mixed together?
It's going to sink. It's going to sink to the bottom.
Yeah, absolutely. And what's the order it's going to sink in? What's going to be at the very bottom, the sand or the mud? What's heavier?
The mud?
So the sand will sink to the very bottom, right? Because
Okay.
the mud is smaller particles. And so it's going to be in the middle. It's like if you think about if you've ever accidentally left a coffee cup out for a long time, and you pour it out at the end of the day, and there's like all of the grounds or like the darker material at the bottom, right? That's kind of stuck to the bottom of the cup. That's going to be the sand in this case. And if you left it out for even longer, eventually the small coffee grounds that are mixed in with the water would fall out as well. And you get like full separation of water, coffee, and then that coffee material. So it's like water, mud, and sand. So if I mixed all of that together and then I threw it on the pavement, what's going to happen to that material? So between the mud and the sand, what do you think is going to travel farther? So remember that the sand is heavier, right? So between the mud and sand, which will travel farther?
The mud?
Yeah, absolutely. The mud's going to travel farther, right? So the sand is going to stop. Oh, I forgot that I always forget that I can draw on Zoom. So I'm going to draw. Here's my little bucket. It's beautiful. I'm going to make sand yellow and just imagine that that's well done. Here, let me make it a little bit thicker. Yeah. Okay. Nobody has the time for me to fill all of this in, so you guys get the point. And then mud is here. And then my water is here. So we're gonna mix this all up with something, and then we're gonna dump it on the pavement. And somebody said, I missed who you were, sorry, that the sand is gonna travel the least amount, and you're totally right. And then comes the mud, right? The mud's gonna travel a little bit farther, like that. And then what travels the farthest? There's only one thing left. What travels farthest? The water. Yes, the water travels the farthest, right? And there are probably some microscopic materials in the water that haven't settled out yet. Actually, or none of it settled, right? Because we mixed it together. But so those microscopic material in the water is going to travel the absolute farthest, right? So the same thing happens with deposits. So you could think of this like a mini turbidity current. Sand is going to fall out first because it's heavier, right? Mud is going to fall out next, and then the little microscopic deposits that are in the water are going to fall out at the very last point. So if I took a sample from here, oh, you could barely tell that from Let's Go Pink. If I took a sample from here, and then from here, and then from here, this will be 3, this will be 2, this will be 1. What am I going to find in sample 2? What sort of material? Or how many materials? If we have 3, right? Sand, mud, and water. How many of those materials am I going to find at 2? Ooh, somebody was speaking, but then maybe got scared. It's not a trick question, right? How many does my sampling cover?
2.
Yeah, exactly. So I'm going to find 2 of these materials here. What about in 1? How many materials am I going to find here?
3.
Yeah, exactly. And then in 3?
1.
Just
Yeah.
one.
Totally, exactly. So what that means, right, is I think we'll all agree from that my 1 is the most poorly sorted, right? My 2 is pretty moderately sorted, and my 3 is very well sorted, right? I've got only 1 material here, so it's well sorted, and here I've got 3. Does everybody agree with that? I'm gonna take silence as yes. I'm gonna put a P here, an M here, and a W here for well sorted. So what can we conclude from that experiment? If I look at some sediment and see that it's all well sorted, can I conclude that it's traveled far or relatively far? Yes or no?
Yes.
Yes, exactly. Perfect. And what if I look at something and it's poorly sorted? What can I conclude? The opposite of this one, right? So it hasn't traveled very far at all, right? So how well something is sorted and the angularity of the grains within that sediment is going to tell you a lot about how far it's traveled. Okay? Okay, awesome. I'm going to clear these drawings. Let's cruise on down. Oh, no. I wonder, can I undo? Please. Okay, yes. All right, so I am going to cruise on down, but I'm going to look at this graded bedding. So this graded bedding or graded beds in general are also going to help us look at what has occurred in the past. So if I take this away, I'm going to take my little bucket away too. So I'm going to imagine that this graded bedding here is just like my little crappy drawing right here. Okay, so if I draw a little box, it's one of my best boxes for sure. Here, and I'll sort of emulate what we see over there. Can you guys see the similarities between my pink box and then this graded bedding box over here, right? It's a little bit different. This has finer stuff here and coarse stuff here, and I've got coarse down here, right, with my sand. I'll say medium grained here with my mud, and then fine with whatever's in my water. But can you see how that's grading from coarse to fine? Same as here, coarse to fine. So it's that same sort of thought process. If I took a sample, or if I drilled a core, or if I saw an outcrop of rocks, and it had this grading from coarse to fine, you can tell a lot about what sort of environment happened to deposit these rocks. So what happened from our experiment with the bucket to make this diagram? What did I do with the bucket?
You dumped the water out.
Yeah, absolutely. I dumped yeah, totally. I dumped it out, right? And I simulated basically a river or a creek or any kind of flowing water, right? So whenever you get this coarse to fine grading, it's some sort of flow. It can be a debris flow. It could be even from wind. It could be from water, but it's some sort of flow. Okay, so graded beddings tell you a lot about what that past environment was to create this sort of coarse to fine material. And again, I get this coarse to fine material from sorting, right? My sand is heaviest, so it's going to settle on the bottom. My mud is second, right? So it's going to settle in the middle. And then the finest stuff is going to be my finest material at the top. Okay? So the same sort of thing happens with turbidity currents in the sea. So it happens in rivers carrying the sediment, and it happens in turbidity currents in the sea. Imagine that, do this. Imagine, it's going to be thinner now, but that this came off of some sort of slope, right? If this is my slope. I want to be able to rotate this. Does Zoom allow that? Probably not. That's all right. This is going to be my slope here. And this is going to be my basin down here. Right? And all of these things came from the slope as a gravity flow. They might have even mixed in a little bit with each other, right? Because they're all tumbling down really, really fast. And then as they hit the basin, this is where they sort of, or they graded themselves out. Sand's going to lose energy the fastest. It's the heaviest, right? Your mud's going to lose energy the second fastest. And then your finer particles are going to go a further distance. Okay, does that connection make sense? From slope to basin, so we're talking about different environments, right? So this graded bedding with this lithogenous material, never mind. I was gonna try to draw lithogenous, but that's gonna take too long, so I'm just gonna write it out. So this lithogenous material, if you see that it's graded, we know immediately about what type of environment it came from, either a river, a sea floor basin, but close to the slope, right? Or some sort of lake possibly, but somewhere where there's flow. Why do I know that lithogenous material must be near the slope or was near the slope at some point in time? Think about
Because it comes from the earth, so it's not like inherently from the ocean.
Yeah, absolutely. So it comes from land, yeah, and you're totally right. There's only so far that this material can travel out to sea, right? So that means that this can't be found right near the Mid-Atlantic Ridge, right? Because how is it going to get out there? So this terrigenous, lithogenous material must be from somewhere near the slope. What are examples of lithogenous material that could be found somewhere random out in the ocean? So if you remember, here was your 3 types of lithogenous deposits.
Volcanogenic from seamounts.
Yeah, absolutely. Volcanogenic and cosmogenic, right? Meteorite fragments. They just go wherever they want. So if I see these two, it doesn't totally tell me a lot, especially cosmogenic. Cosmogenic doesn't tell me anything about the depositional environment because, like I said, they just are random, right? But terrigenous is going to tell me, okay, this derived from land. So I know that this point on my, or in the ocean basin, must have been close to the seashore, must have been close to the continent. Okay. All right, cool deal. I'm gonna clear this drawing and let's cruise down. So what you guys are going to be doing is here's your data. Notice, right, that these are the same data, same material. It's just this is a lot more zoomed in. Okay, same thing, same material, just a lot more zoomed in. All right, so you guys are going to be looking at this material and figuring out sort of the depositional environment about where they would have come from. So for example, this quartz sand, which is from Fort Pierce, Florida, you'll notice that it's all made of the same material, right? And that these grains are relatively well-rounded. They're a little bit angular, but they're pretty well-rounded, right? So rounded and well-sorted, what does that mean as far as how far they've traveled?
Very far.
Yeah, absolutely, absolutely. What about this shell and rock fragment from California?
They probably not traveled as far.
Yes, absolutely. Good. Awesome. So that's going to be part of this lab, is looking at this data and figuring out how far they've traveled and also what type of margin they came from. And by margin, I mean active margin, right, where there are active tectonics going on, or a passive margin. So let's look at some examples of both, okay? So we, on the East Coast, do we live on an active or a passive margin?
Passive.
Absolutely, we live on a passive margin. Good. So let's just look at the US from this far out. What do you guys notice immediately? Actually, we're going to zoom in just a tiny bit. What do you guys notice immediately about the continental shelf on the East Coast versus the West Coast?
It's flat on the East Coast, and everything out west kind of looks like mountainous.
Yeah, on the continent for sure, but out in the ocean, I mean, the continental shelf is a lot thicker, right?
Yeah.
Yeah, absolutely. So it's a lot thicker because it's on that passive margin. Over here, remember, we've got this transform boundary here. And then right about here, it ends and becomes a convergent boundary, right? It's a subduction zone. So all of that continental shelf material is basically just being eaten by that subduction zone, or it's being disrupted by earthquakes. And so that continental shelf material is being displaced, it's being disrupted, and it's not being allowed to build up, right? There's no reefs over here. It's too tumultuous. However, over here, there are a ton of reefs, right? Because it's a shallow, warm, passive margin. We can also look at other margins around the world and see the same thing. So let's go over, sorry. I'm gonna zoom way out. So let's go over here. Are there any plate boundaries up here? No, exactly. And look at how big this continental shelf is. Are there any plate boundaries over here? No, you're right. But this shelf isn't super big, right? Why is that? That's a great question that I don't know the answer to. But if we maybe go over to South America, we still see this difference over here, right? Passive margin, active subduction. And in fact, we can see the trench, can't we? Which is pretty crazy. So tons of earthquakes over here, tons of disruptions, really quiet over here, big shelf. Oh, you know what, actually, I think I do know why there's no continental shelf over here. It has to do with the current. So the current, yeah, I think it has to do with the current. Here the current is coming from, I think it should be coming from the Antarctic. And so it's super cold water that does not allow any sort of like coral reefs or anything to form. So there's nothing to build up that continental margin. But I'll double check about that, but that would be my hypothesis. But over here, right, we've got water stemming. We've got lots of, what's like the most famous thing about Brazil as far as geography goes? What's that huge river? It's this one. What's it called? Do you guys
The
remember?
Amazon.
Yeah, and exactly. So a big feature of passive margins are really long continental rivers. So here we've got the Amazon. What about over here? Do you guys know of any super long rivers over here? No, you shouldn't, right? All of these rivers come straight from the Andes. They're really, really relatively short, and they don't have enough time to collect a lot of sediment. What about over here in this part of the US? Do you guys know of any really long rivers? The Columbia could be considered a longer river. And in fact, if we zoom in to where the Columbia River comes out, we do have a little bit of buildup, don't we? And then we've got this long canyon right here where sediment goes, right? But it doesn't have anything on the eastern part of the US, does it? And think of all the huge rivers we have over here, right? Missouri to the Mississippi. We've got tons of long rivers. There's 4 pretty huge ones across Virginia. There's some long ones that I forgot the name of that go straight through Georgia, right? And they all stem from the mountains, yes, but different tributaries off of either the Mississippi, the Ohio River, and I forgot the one that goes through Georgia, forgive me, but it's this one right here. Right, so you've got longer rivers on the passive margin sides, right? Longer rivers mean longer sediment transport times, which mean more well-rounded and more well-sorted material. Over here, we're on active margins. You have rivers for sure, right? But they're carrying sediment from a relatively close distance, right? The Sierra Nevada, the Sierra Nevada, Mount Hood, Mount Shasta, Mount Rainier up here. And they don't have really a ton of time to settle out on the continental shelf, right? Again, because of the active tectonics that's going on. Does that make sense? Does that correlation make sense? Okay, so just to throw a wrench in that, what about sediment deposits from places like Hawaii? So what is Hawaii again? It's a hotspot, right? And so it's a hotspot, and that hotspot is made from, it produces rocks that are all the same type. It's just basalt in Hawaii. There's no other rocks, maybe some shell fragments, but that's it, right? So that same source rock, that basalt, is going to create the same type of lithic material, right? It doesn't matter how far it's traveled. So you can get things that are well sorted that have not traveled a long distance just because that's all that is there. Okay, so you might get some well sorted sand, but has maybe some sharper angles, right? Or maybe it even is a little bit rounded just because of, mineral decay or something like that. But so the well sorted and well rounded features of sand can tell you a lot about environment, but you got to double check with other things to make sure that what you're saying is correct, right? Because Hawaii really throws a wrench in things. Iceland is the same way, right? It's a lot of basalt, some rhyolite, right? But it's all basically from the same material. So you're going to get well-sorted sand that actually hasn't traveled a far distance. Okay. All right. Well, that is it for today. Let me know if you guys have any questions. I'm happy to answer them. If not, then let me know throughout the week. Cool.
Thank you.
Yeah, no worries. Just a reminder
Have a
that,
good one.
yeah, you too. I've pushed back the lab due dates till Sunday. But I'm actually definitely not going to answer any questions about it on the weekend because I value my mental health. Okay, cool. See you guys later. Unless you have questions, and then stick around. Okay. Hey, Lily.
Hello.
So did you find the website and everything?
Yeah, I found all the stuff. I watched
Okay.
some of the videos this morning, and I